I will start with a word of prayer. Hem. Dear Father, we thank you for this day. Just pray you'd help us to use this time wisely, that you'd just help us to round out our understanding of integration, and just to make good use of this time, Lord. In your name I pray. Amen. So you guys have a test when? Next Tuesday, right? Thursday. Oh, Thursday, yeah. Yes? Attendance. Attendance. Not time to ask about attendance yet. What's that? What's that? Oh, it was a legitimate question about attendance? Well, thank you.
You were saying that the person to see a hand raised would just be about attendance.
Yes.
What is that?
So he was trying to...
Yeah, we're going to say agree for later. Thank you for that.
Let's see here. All right. So...
Disease has spread beyond the Joshes.
This is... All right. All right. Of all the stupid ways to waste class time to talk about attendance. Anyway, it's not your fault. Anyway, I know I had a sheet we handed around yesterday, but just for the sake of keeping it all in one place, if I got 328 and 329 on here, so you mark both. I assume you can remember whether or not you were here yesterday, so yeah. Okay, so I pushed the homework back to Tuesday, partly so that I'd have time to share with you guys some examples today, which I think should help round our understanding of what we're doing out. So I'm going to do about 5 examples today that they're kind of medium difficulty. All right. Example 1. We want to calculate the triple integral of, let's say, x squared plus y squared dv. So we could say dx, dy, dz if you like. Over the region W, to calculate this, given W is bounded by x squared plus y squared equals to 1. And let's see here. How about x plus y plus z equals to 10, and z equals to minus, well, how about z equals to 0. There. All right? So we want to calculate this integral. Now, I will tell you, the region we're talking about here looks like what? I mean, x squared plus y squared equals to 1 is a cylinder, right? So down here maybe z equals to 0, right? And then what's x plus y plus z equals to 10? It's a plane, right? I don't know what it is exactly, but something like that, right? And so it's cutting through that, like there somewhere. And so essentially, we've got like a partial cylinder where we've got a horizontal cross-section for the bottom, and we've got kind of like a tilted cross-section for the top, right? So I think the best way to describe such a volume is in terms of cylindrical coordinates, right? So in cylindrical coordinates, we can see that W is described how? It's described by 0 less than or equal to theta less than or equal to 2 pi, right? We sweep all the way around in this region. And how about R? Well, it looks like R is ranging from what? 0 to, oh yeah, 0 to 1. Yeah, I'm an idiot. 0 less than, like, what's R ranging? Maybe this was a clue. I mean, that's technically R squared being 1, but if R squared is 1, then R is 1. So if we were just to think about sculpting all of space with those, Well, first of all, if you say 0 less than theta less than 2 pi, have you removed any of R3? You have not. I mean, sweeping theta all the way from 0 to 2 pi doesn't really do anything, right? It just says everything, all directions are possible. 0 less than r less than 1, that actually that gives us the infinite cylinder with radius 1, right? Well, cylinder, yeah, cylinder. Now, to actually cut it down to just what we want, right? To cut it down to just the region we're interested in, namely this thing, right? To cut it down to this shape, I need to put the z up and the z down. And any z between those, right, is going to be between those two things in the shape we're interested in. So we have 0 less than or equal to z less than or equal to z up, right? But what is z up here? 10 minus x minus y is a good starting step. But the trouble with that, of course, is that is from the world of Cartesian variables, right? Which is not quite what we want. Yeah, safe enough. Wow, my aim is really off. I mean, he's all the way over there. He's like, why do you think I'm sitting here? Let's see here. So in terms of polar coordinates, that becomes 0 less than or equal to z, excuse me, polar coordinates. In terms of cylindrical coordinates, 0 less than z less than 10 minus r cosine theta minus r sine theta. All right? So now we have done the groundwork that we need to do this integral in cylindrical coordinates. All right? So our integral, which I'm going to relabel as f dv. So the integral of f dv over this region w, in cylindrical coordinates rather, I'll get it right eventually. We've got 0 to 2 pi. We've got r going from 0 to 1, right? But then the z bounds are interesting. Those go from 0 to 10 minus r cosine theta minus r sine theta, right? And then I need to do what? Remember, there's 3 things we had to do. We had to change the integrand, we had to change the bounds, we got to change the measure. So I did the bounds, now I have to change the integrand. The integrand is what? In terms of polar coordinates, that's what? Cylindrical coordinates, yes, but polar. I'm not wrong, I'm just not right. Okay, r squared, because I'm trying to say cylindrical. All right, and then how about this? What's this in terms of cylindrical coordinates? We worked that out. That's r. Yeah, but unfortunately here I should write r dz dr d theta, right? So this will give us the integral from 0 to 2 pi, the integral from 0 to 1 of r cubed times 10 minus r cosine theta minus r sine theta, dr d theta. The reason for that is I'm just integrating dz, right? The integral of dz gives me z. And z evaluated from the lower bound to the upper bound just gives me the just exactly this. So this is the z integral just works out to what I have in parentheses, okay? I'll make one more step before I go further. This is the integral from 0 to 2 pi, integral from 0 to 1 of 10r cubed minus r to the 4th cosine theta minus r to the 4th sine theta, dr d theta. That's really the integral from 0 to 2 pi. And the 10r cubed integrates to 10 fourths. The r to the 4th, that gives me a 5th, so I get 1/5 minus 1/5 cosine theta minus 1/5 sine theta d theta. But Not particularly. In fact, integrating the d theta first would have revealed something. If you'd integrated d theta first rather than dr first, you would already discovered that both of these things go to 0. Because if we integrate sine or cosine over a full cycle, they cancel out. Right? There's an equal amount of positive and negative area under sine and cosine from 0 to 2 pi. I don't need to write more. I know those go to 0. In fact, I knew that back here, but I just didn't do it because I thought it would confuse you guys. Oh, well, anyway. So this gives us 10/4. And then this theta, here I'll actually write one down. Are you happy? 0 to 2 pi. So that gives us 10 over 4 times 2 pi, also known as, I think, 5 pi over 2, right? There you go. No? What'd I do? Oh, yeah. Thank you. Anyway, is the technique here clear enough? You could ask the question, so when I have a problem that's, a triple integral, how do I know that I should use cylindrical coordinates, right? How do I know that I should use spherical coordinates? Like or should I use something else? Like, how do you decide what change of variables, if any, you should make? I think as a default, you try to use Cartesian variables, right? But if in the process of setting up Cartesian variables, you find out that you've got square roots and stuff in your bounds, you got to think, maybe there's a better way to do this, right? And so that would be my, so I would, for me, when I look at a problem, the integrand is of secondary importance to the bounds. To me, the bounds pretty much, I want to face the bounds. Usually the bounds are what will dictate my choice of coordinates. These bounds are essentially cylindrical in nature, right? So next topic is centroid and moment of inertia. So for a volume, I'll call the volume W since that's kind of the letter I've been picking on lately. So the idea is you're given some solid object. We'll call it W, all right? And it has got two S's. That's not wrong, not right. It has mass per unit volume, aka what? Mass density. And the letter I've been using, I think, in your notes. Shut up. Not you guys. What's this? Mass density, delta, is equal to dm dv. It's the mass per unit volume. In physics, this is often denoted like rho, okay? Or especially in electrostatics, we'll use rho for charge per unit volume. You can see why that would be a bad choice here, because we use rho for radius. So I got to use something else. So I use delta for the density, all right? The mass per unit volume. So once you have this, you can do things like, what's the total mass? It would be the triple integral of dm over the shape, right? That would be total mass. Okay, great. Well, how do you actually calculate? What do you mean integral of dm? What does that even mean? That is an invitation to be logical. And so you change it to the corresponding triple integral, which makes sense to you, namely delta dv. Right? See, because if delta is dm dv, that means that dm is what? Is delta dv. All right? And so to calculate the total mass of an object, we integrate the mass density, the mass per unit volume, over the whole volume. This delta could be a function of position. Often, it's just a constant, but it doesn't have to be. One of your homework problems, that delta is rho to the power c, where c is an arbitrary constant, right? For example. That's total mass. Then you can calculate what's the average x. The average x average. Well, the average x would be 1 over the total mass times the triple integral of x dm. So this is I would say that this is a weighted average, but that's not quite average. If you want me to make this a weighted average, all right, you want me to make it a weighted average? Fine. You just got to put like a g here, and you got to put like a g over here. Then that would be a weighted average. Physics humor has a very small audience. I should stop. So, yeah, because mg is weight. Yeah. But anyway, so yeah, this is a sort of almost weighted average. So what does that mean? Well, this actually means how you actually calculate that is 1 over the total mass, the triple integral over w of x delta dv. So that gives us the average x value. How do we find the average y value? 1 over the total mass, integral w of y delta dv. And, of course, the average z value, 1 over the total mass, integral over w of z delta dv. Altogether, x bar, y bar, z bar is the center of mass for w. All right. So if you're asked to calculate the center of mass for a given solid object with a given density, you should realize you've just been asked to do 4 triple integrals. You should be happy. Triple integrals are fun. What's wrong with you guys? What do triple integrals ever do to you? You know? Oh, I guess they are doing to you right now. But listen, what's the centroid? Centroid is basically the geometric center. Geometric center of W. You can obtain by setting the density equal to 1. If you set the density equal to 1, what does that mean? The mass actually means what in this context? If the density is 1, what's the mass actually? Right, it's actually just the volume of W. Right. And then these actually become literally average value of x, average value of y, average value of z over the solid. Right? To find the average value of x over a solid, you take the sum of the values of x over the volume, and you divide by the volume. That's the average. Just like in Calculus 1, we took the average of a function. We took the integral from a to b of f of x. We divided by b minus a, which was the length. That gives us the average of f of x. Well, similar ideas apply to triple integrals. We can average quantities over volumes using this idea. Okay. I think it's important for us to have this discussion. Now, that said, you do get a 3x5 card for your next test. May I encourage you that perhaps these are things that should find their home, unless this talk has forever cemented it in your mind what I just said. Yeah, okay. So, now, so I have not talked about the moment of inertia yet. Moment of inertia has to do with rotational motion. And so basically the idea is if you got some shape, blah, 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 shape, right, and you got some axis, right, And suppose the shape rotates around, it's a rigid body. And suppose that that rigid shape rotates with angular velocity omega around the axis. Okay, maybe it doesn't make a noise, but it could be in space. So unless you're in a movie, it won't make any noise. And then the question is, what's the rotational kinetic energy of this thing? The rotational kinetic energy is equal to 1/2 I omega squared. So moment of inertia for a solid has to do with rotational kinetic energy. It plays the analog of mass for rotational kinetic energy. There's also a formula that the torque is equal to I omega. So it really, just like force is equal to mass times velocity. The moment of inertia for rotational physics is analogous to mass for linear physics, right? So how do you actually calculate the moment of inertia for a solid? So with respect to the z-axis, the moment of inertia for like W would be equal to the integral over W of r squared dm. This is the continuous, now if you've studied physics, I don't know if you have or not, but if you have, this is the continuous extension of, what's the formula? The moment of inertia for a single mass, it's r squared times m. That's moment of inertia for a point particle. So this becomes the little infinitesimal moment of inertia is r squared times dm. That's the moment of inertia for just a little mass at distance r from the axis of rotation. So to find the total moment of inertia, we just add those up over the volume. All right? Anyway, for you guys, this is essentially definition. Again, how do you calculate an integral over dm? You don't. What you do is you convert this to the appropriate volume integral. The appropriate volume integral is precisely the integral over W of x squared plus y squared, right, delta dv. Or maybe you want to stick with r squared because maybe the shape is cylindrical in nature, so cylindrical coordinates are a good choice to actually calculate the integral. I don't know, right? Okay, but these are what centroid, center of mass, and moment of inertia look like with respect to the z-axis, right? What would moment of inertia with respect to like the x-axis be? So I got something, and it's spinning like that. X-axis, what would that look like? Not the same thing, no. X squared, y squared plus z squared, we have a winner. Yes, it's the whatever variables are not the axis variables, because those tell you how far the little bit of mass is from the rotational axis. Yeah.
So it still would be r squared, but r squared would be...
It's still r squared, but r is not the same r. Yeah. By the way, you know, you can set up non-standard spherical and non-standard cylindrical coordinates where you trade the role of z for x and so forth. I mean, you can switch there's other coordinate systems that are sort of, I would call them for our purposes like pseudo-spherical or pseudo-cylindrical, non-standard cylindrical, non-standard spherical coordinates where I, set up the measure of theta and phi differently or something like that. But one thing at a time. So let's actually do one of these. Let's calculate the moment of inertia for a sphere. Yeah.
Real quick, for inertia equals to triple integral of r squared dm.
Yeah.
I know that dv deconstructs into dz, dy, dx.
Yeah.
What would dm deconstruct into for spherical coordinates?
Well, again, dm is delta dv.
But
Yes.
if you keep r squared as spherical coordinates, does that mean? Oh wait, then you just turn dx, dr.
I mean,
dy.
we still have dv. You have several flavor options: dx, dy, dz. always popular. You have your r dr d theta dz, sometimes popular. And then you have the dreaded rho squared sine phi d rho d phi d theta. Them's our usual choices for dv. I think that, and does that answer your question?
Um,
We'll think about it.
I was wondering what, because that would, for dm, if you were to use the first equation there, it would be 1 over those.
dm, first equation. What first equation? First equation. Which first equation?
Oh, right over there. Because you said,
dm.
like if you wanted to make it spherical, you can just stick with that. So I was wondering how you would make turn dm into a dx, dy, dz, or rdr, d theta.
I mean, I suppose dm you could write as delta dx, dy, dz.
Okay.
Sure. But I prefer not to. I prefer to think of it about it. I like to think about dv. To me, the concept of dv on its own is useful because I'm not committing to Cartesian, cylindrical, or sphericals at that point. It's the volume element, which geometrically exists independent of our choice of coordinates, is the idea. Yeah. So how about a sphere? Constant density, delta, of radius r. What's its center of mass? Don't like my picture. Anyway, sphere. I never decide where I want to put the radius r anyway. Okay. What's the center of mass for the sphere? If you think about these integrals, right? You'd be integrating x over the whole volume. There's an equal amount of positive and negative x. There's an equal amount of positive and negative y. There's an equal amount of positive and negative z. The center of mass for the sphere is the origin. We don't need calculus to figure this out, right? Just saying. Center of mass is clearly 0, 0, 0, by symmetry, if nothing else.
But do we know from what you've given us that we are indeed centering about the origin? Is that assumed if we don't give another center?
Well, I said, well, yeah, if I just say a sphere of radius r and I don't say otherwise, I'm assuming it's centered at the origin. But you're right, I really should say centered at the origin, because if the center was not the origin, the center of mass would be the center of the sphere wherever else it was. Indeed. Okay, but the moment of inertia is interesting. We can still calculate that here, and let's do that. All right, so moment of inertia about the z-axis should be the integral, triple integral over the sphere, right? So the sphere is really what? It's the spherical radius less than or equal to r, is it not? I mean, if I wanted to describe the sphere succinctly, I could, or fine, tell you what, x squared plus y squared plus z squared less than or equal to r and greater than or equal to 0. It's the set of x, y, z such that that holds. That's the sphere, right? And to calculate the moment of inertia, I'm supposed to calculate what? X squared plus y squared delta and then dv. Actually, I'm going to put it down here. So let's see here. That's actually the integral from what? From 0 to 2 pi, the integral from 0 to pi, the integral from 0 to r, right? Those are the bounds, right? A sphere, it sweeps out the full range of theta, the full range of phi, and the r is going, I mean the radius, the spherical radius is going from 0 to big R, which I'm taking to be a fixed positive constant here, right? The same is true for your homework problem, is that right? I think I have a homework problem where r is a fixed but arbitrary constant for the problem. So like the answer probably involves r. Okay. Okay. Now here, we've got x squared plus, what is x squared plus y squared? It's r squared, like this cylindrical or polar radius squared, right? So x squared plus y squared equals to r squared. Now, if I'm using spherical coordinates, that's not what I want there, right? I need to recast that in terms of spherical coordinates. What's r in terms of rho and theta and phi? Do you remember our picture? Right. This down here, rho sine phi, because this is rho, and that's phi because this is phi. Right? So r. So really, what I have here is I have rho squared sine squared phi, right? That's that. Then what's dv? Well, there's the delta, which is a constant. What do we do with constants? Take them out, right? It's very violent. But we'll just exile it to the front of the integral. So it'll live on outside our borders. Oh, okay, so, and dv, well, that is rho squared sine phi. And now I got to be careful. D rho, d phi, d theta. I'm taking off the gloves. This is delta times 2 pi times r to the 5th over 5 times the thing that actually requires some calculation here, integral from 0 to pi, sine cubed phi d phi. I did the integral over theta. There's no theta function. D theta integrates to theta. Theta evaluates from 0 to 2 pi to give me a 2 pi factor. I have a net of rho to the 4th. Rho to the 4th integrates to rho to the 5th over 5. Then when I evaluate from 0 to r, that gives me the r to the 5th over 5 factor, right? Beware of these kinds of steps when you have variable bounds. If we don't have variable bounds, I can get away with it. If you're not comfortable, do it step by step. All right, now sine cubed. Let's focus on our sine cubed integral. How do we do integral of sine cubed? Do you guys remember? I'll do it over here on the sideboard. Let's see here. Integral of sine cubed phi d phi equals to the integral of 1 minus cosine squared phi sine phi d phi, which is the integral of 1 minus u squared times minus du, letting u equal to cosine phi, which is the integral of u squared minus 1 du, which is 1/3 u cubed minus u plus a constant, which is 1/3 sine cubed phi minus the sine of phi plus a constant. So that's why this integral, the sine phi, oh, wait a minute. I got to think about this. Oh, it actually all matters. All right, anyway, so I'll write down here. What do I got? I've got delta times 2 pi r to the 5th divided by 5, and then I got to calculate, what did I work out to? I can't find my glasses right now. It's very bad. 1/3 sine cubed phi minus sine phi. I feel like that's wrong.
Yeah, because you plugged in u as sine phi when you said u was cosine.
Yeah, my hint for it being wrong was this was working out to 0, but I think I stated a u substitution.
Yeah, you did.
But then in my fury of calculation, I forgot a basic, point of logic. Let's see here. So moral of the story, don't hurry. anyway, so what happens with this when we plug in pi? We get 1/3 minus 1 plus 1, and then the 0. What happens with 0? 1/3 minus 1, right? So we actually get 2/3 plus 2/3 from the sine cubed integral. In other words, this sine cubed, some of you have been like, I'm just looking at it. I think that's 4/3, right? I mean, if you could eyeball that integral and tell me 4/3, I'd be like, whoa, you're really good at calculus too. So anyway, it is 4/3 though. And so what happens with that is we get what? Two pi delta r to the 5th divided by 5 times what? Times 4/3, right? Do you guys recognize that formula from physics? I sure hope not. I sure hope you don't, because that's not how we write it in physics. How do we write it in physics? You look at your table of moments of inertia. What do you see? You see mass and radius, right? So to make this formula interesting, we should restate it in terms of mass rather than density. So we've calculated that I is equal to, what is it equal to? 2 pi delta r to the 5th over 5 times 4/3, right? Notice that mass is equal to the integral dm over the sphere, right? But that's equal to the integral over rho less than or equal to r of dv, right? Did we work out what the volume of the sphere is yet? I don't think we have. Let's do it. So this is the integral from 0 to 2 pi. Oh, I'm sorry, I forgot my delta, right? Delta dv, right? Josh asked me all these questions, and I already forgot. Delta dv. Now the delta is a constant here, so pull it out. Integral from 0 to 2 pi, integral from 0 to pi, integral from 0 to r of rho squared sine phi d rho d phi d theta, which gives me delta, integral from 0 to 2 pi of d theta, integral from 0 to pi of sine phi d phi, integral from 0 to r of rho squared d rho. Is question? You're wondering where the rho squared sine phi d rho d phi d theta came from?
Yeah.
I forbid this question days ago. How dare you? Sorry. That's high school. No, wait a minute. No, it's not high school. That's at a good high school. Sorry, there was this well-known Calculus 2 professor at NC State who, if you asked him a question in the middle of his lecture, he would like slowly turn around, glare at you, and then go, "That's high school." And then he wouldn't answer your question. He'd go back to his lecture, and he's famous for this. So, yeah, it does sound pretty terrible, but hilarious. I also experienced this in one of my, I had differential equations class with a similar thing. The engineers in there, mostly engineering students at NC State, they'd ask questions about whatever, but he basically did the same thing, but he was super chill about it. He'd like turn around and be like, "It's just algebra, man," and then he'd go on. So it's really the same, and yet not the same, right? But this professor was awesome. He looked a lot like Morgan Freeman, actually. And he was still wearing like drawstring pants at that point, because I think his wife bought his clothes in the 70s probably. But anyway, yeah. No? Was there a question after that? It's a long calculation to show that the volume element, this is the volume element in sphericals is all it is. That's the dv. It's over there. Yeah.
We're solving for the mass of the sphere.
Indeed. So the mass of the sphere is delta. And what does this work out to? 2 pi, 2, and this is r cubed over 3. So what you got is you got delta times 4 pi r cubed over 3. This is really not surprising. If the mass density is constant, then the density times the volume gives you the mass. What's the volume of a sphere? Well, we just derived it. It's 4/3 pi r cubed. Let me repeat that. We just derived the volume of a sphere. Yay! Right? And it was easy, actually. It was not bad. It's easy if you ignore the pain and suffering that went into calculating the spherical volume element, right? Which actually was a little bit. Okay, so then now that we know this, we can solve for delta. What's delta? And this is very unsurprising when I write it down. Delta is equal to mass divided by 4/3 pi r cubed, right? This is like, duh. So you mean so what I'm trying to tell you is that for a constant density, the average density is equal to the infinitesimal density. The total mass divided by the total volume is equal to delta, which is by definition dm dv. This is not surprising. But, so you can take this, right? Take this right here and put it up into here. What do we get? Can you see, is there a copy of m fine, I'll just write it out. 2 pi r to the 5th times 4 divided by 5 times 3. And then what's my delta? My delta is equal to m divided by 4/3 pi r cubed, right? So if you allow me to erase the start of this. Oops. Oh well. So what's this work out to?
2r squared over 5.
Yeah, I think 2/5, right? 2/5 mr squared. So there you go. That's the moment of inertia for a sphere. 2/5 mr squared. Now, your homework problem will be a little bit different, right? Because in your homework problem, your delta, rather than just being a constant, is alpha rho to the c. There's a homework problem like that, right? Where alpha is a constant and c is a constant. So essentially, this problem I just worked, we put c equals to 0 and delta is just alpha. Or you could say alpha is delta. I don't know. But I hope that helps you with that homework problem a little bit. Yeah? Any questions? Yep.
Going back really far, you may have already explained.
That's fine.
When you're setting up the bound at the very beginning,
Mm-hmm.
why is the only 0 and pi not 0?
Because that's the way that angle works. I mean, phi equals 0 is up here, right? And then it swings all the way down here to phi equals to pi. So it's because it swings that way. It swings directly off an axis in that way. I mean, it's not like the polar angle is defined differently. I mean, phi and theta, yeah, they're both angles, but they're really different in their geometric origin as they relate to the coordinate systems.
If it ended up being on the other side, then it would just be that.
Yeah, right, over here. Yeah, if phi goes to pi, and then if you go past that south pole, you start swinging to values less than pi again. So, I mean, another way to tell this story is if you pick a point in space, like here, right, then the way it works is I start with my theta equals to 0, right? I take that point, and I project it down to the xy plane. I see how far I have to swing over in the xy plane. That's my theta, right? But then, on the other hand, I take my z-axis, and I see how far I have to swing this way to get my phi. So the difference is the theta involves a projection of the point onto the plane, whereas the z-axis angle does not. So geometrically, if we take our position vector dotted with z hat, well, that's equal to the length of the position vector, which we call rho, right? Cosine phi. So that's cosine phi. On the other hand, theta describing theta in terms of theta would not be so quickly defined. I'd have to think about it a little bit more to give you a dot product, blah, blah, blah. I'm digressing. Let's move on. Is there a question about the integral? Okay. Here's an example I try to do. What if you were going to calculate volume of x squared over a squared plus y squared over b squared plus z squared over c squared less than or equal to 1? See, this is an ellipsoid, right? A solid ellipsoid. It's something like that, right? Now, if I was trying to do that directly, it's kind of a drag. But what you can do is something sneaky. You can invent new coordinates, u, v, w, right? And change this so that it's like u squared plus v squared plus w squared less than or equal to 1, right? This is straight up the unit sphere, right? In UVW space, right? What's the volume of the unit sphere in UVW space? It's 4/3 pi by the thing we just did, right? If the radius is 1, the unit sphere has volume 4 pi over 3. So what coordinate change am I suggesting? Can you guys tell me? How about this? X over a equals to what? U, right? Y over b equals to v. Z over c equals to w. So we have x is equal to au, y is equal to bv, z is equal to cw. And so we can calculate our Jacobian, partial x, y, z, partial u, v, w. What's that? Partial derivative of x with respect to u is what? A. What's the partial derivative of y with respect to u? Yeah. So you quickly work out that this is the matrix for the Jacobian determinant. So the Jacobian in this case is just ABC, right? And so to calculate that volume, we do the integral. So the integral, stink. Oh, fine. So the integral x squared over a squared plus y squared over b squared plus z squared over c squared less than or equal to 1 of dv. That would be the volume, right? The integrand here is just 1. So now I need to change the integrand into UVW coordinates, right? How do you change 1 into UVW coordinates? Still 1, all right? So that's not exciting. How do you change dv into UVW coordinates? Remember, dv, on the one hand, it's dx, dy, dz, but it's also equal to partial x, y, z, partial UVW, absolute value, du, dv, dw, which in this case was a, b, c, du, dv, dw. But ABC is a constant. We can pull it out. So what's the answer? What's the integral of u squared plus v squared plus w squared? less than or equal to 1 du dv dw. What does that mean? This thing I just boxed in green. What is this? That is the volume of the unit sphere, which is what? Yeah, 4 pi over 3, right? So the answer here is 4/3 pi ABC. That is the volume of an ellipsoid. Which makes a lot of sense if you think about the most special kind of ellipsoid, which is what? A sphere. Sphere is when A is equal to B is equal to C is equal to, well, usually R for us, right? That formula becomes what when A equals B equals C equals R? Right, 4/3 pi r cubed. That's the volume of a sphere. This is kind of a nicer coordinate change than the one we looked at yesterday, right? All right, now that I've blathered on about triple integrals at some length, all right, let me turn the page back and tell you a little bit more about integrals in the plane, right? So my example here, which is example, I forgot the number of these stupid things. Example 4, all right, thanks. Let's find centroid of Pac-Man. So here's going to be my Pac-Man. There we go. And I feel like this should be theta equals to pi over 6, and this will be theta equals to minus pi over 6. And will this be a unit Pac-Man? So, distance 1. I won't bother with the I, right? To make a more sophisticated Pac-Man problem, add an I that we have to remove, So centroid of the Pac-Man. So to calculate the centroid of the Pac-Man, you have to calculate, first of all, what's the area of Pac-Man? Oh, sorry, no I. Right, so that would be what? The integral over Pac-Man of dA. And the x bar would be 1 over the area of Pac-Man, integral over Pac-Man of what? X dA. Y bar, 1 over the area of Pac-Man, integral over Pac-Man of y dA. These are, do you see that? I mean, it's the same stupid thing I was doing over, I erased it, but over here for volumes, right? To calculate the centroid of a volume, we do the triple integral over x and divide by the volume. To calculate the average x for an area, we calculate the double integral over x and divide by the area. And likewise for y. If you wanted to talk about center of mass for a plane, what would we do? We have to adjust with a mass density. I usually use sigma for the mass per unit area. There might be a problem like that in your homework. If there isn't, I'll try to make sure I put one on the math battle for you guys to look at. Okay, so how do you actually calculate these? Actually, this problem is actually too easy. I'm a little bit disappointed in my example because this Pac-Man's too easy. It's what it is. I mean, because it's fairly clear that the way to describe Pac-Man in polar coordinates is 0 less than r less than 1, right? And what about theta? Pi over 6 less than or equal to theta less than or equal to? Well, you could write minus pi over 6 there, but you'd be wrong. In concept, you'd be right. I mean, it's the minus pi over 6 you're going to, but if we're going to write it in this interval notation, interval kind of idea, we need to put what? 5 pi over 6, right? You got to watch out for that issue. It'll rear its head when you're not expecting. And Thank you. I guess I was fished in. Anyway, so the area of Pac-Man would be the integral from 0 to 1, integral from pi over 6 to 11 pi over 6, right, of r d theta dr. And not surprisingly, that works out to what? 1/2 times 1 squared times 11 pi over 6 minus pi over 6. In other words, 1/2 of 10 pi over 6, which I believe is 5 pi over 6. I say not surprisingly because really if you look at what we just did, that's just deriving the area formula for a sector, right? I mean, we're really looking at a sector of a circle where we've just deleted that one sector from, I mean, it's, anyway. So that's the area. How about the x bar? So it should be 6 over 5 pi, right? Integral of what? R cosine theta times r dr d theta. So my r goes from 0 to 1. My theta still goes from pi over 6 to 11 pi over 6. So I've got 6 over 5 pi. What's sine? Cosine theta integrates to what? To sine theta, right? Sine theta evaluated from pi over 6 to 11 pi over 6. And then what's my r do? I've got r cubed over 3, right? Evaluate that thing from 0 to 1. I'm disappointed because I wanted to show you guys something with polar bounds which was a little bit harder than this. I guess I could just put it on the daily quiz tomorrow, right? I'm sorry, I keep forgetting we don't end at 150. I was thinking we end at 150. I thought it was up a creek, but actually we're fine. We're fine. Fine. So what's sine of 11 pi over 6? I had to think about this. Sine looks like this, right? Whee! So pi over 6 is here, right? Sine of pi over 6 is 1/2. So 11 pi over 6, yeah, sine of that. So this actually is altogether -1. Because it's -1/2 minus 1/2. And this is 1/3. So we get 2. I think we get -2 over 5 pi, yeah? What's y bar? I heard a small but sure 0. Right. Why is y bar 0? Exactly. By symmetry, y bar equals to 0. So thus the centroid is at -2 over 5 pi, comma 0, which makes a lot of sense if you just look at the picture for Pac-Man. It makes sense that the center is, you know, what is -2 over 5 pi? It's like 2/15. What's 2/15? It's a little bit smaller than 3/15, right? 3/15 is 1/5, which is 0.2. So it's like minus point. I don't know. It's yeah. Oh, a little bit bigger than 1/15. A little bigger. Yeah, a little bigger than 1/15. Also true. So it's somewhere in here, roughly speaking. Yeah. Centroid.